Welcome to this section of the course where we're going to talk about the derivative and the integral of the exponential function. You see, the first part of the class, the whole DVD set here, we've talked about how to take a derivative of the fairly basic functions. And then I taught you how to take the derivative or rather the integral of the fairly basic functions. And now we're getting into a little bit more of the advanced stuff, and we're going to go backfill and show you how to take the derivative and the integral of some of the more complicated function like exponentials rather in this section, and then later on logarithms and other things. And so we're going to get into some of the, well, it's not really any harder, it's just different rules you have to look at. So let me go ahead and explain that to you right now. And you might want to write some of this down, or maybe you'll have your book open to this section and maybe you'll see it. I'm going to write some properties kind of over here. It's not going to be too many properties, by the way. And like we've been doing through the class, I'm going to leave them up here, and we're going to end up using them as we go over here, and hopefully you'll remember them. It turns out that the exponential function is actually quite easy. It's very, very simple to remember what the derivative of the exponential function is. The derivative with respect to x of e to the x, remember e is just a number, 2.7 something, raised to the x power, this is called the exponential function, is equal to, you ready? Drum roll, please. E to the x. Doesn't that look weird? The derivative of the exponential function is the exponential function. It's called the indestructible function. You can't get rid of it. You take derivative of exponentials all day long, and you can't get rid of it. Don't fall into the trap of trying to say this is x times e to the x minus 1. That's not going to work, and that's not true. Okay. The formula for the derivative of like x squared, you take the exponent out, and then you have x, and you put 2 minus 1 would be 1. Well, that would be the answer. This is the derivative of an x raised to a number. This is a number raised to x. Okay, and specifically, this is a very special number. It's e. Okay, so e raised to the power of x, take the derivative, get the same old thing back. It really isn't that bad. Okay, now because of this, the antiderivative of e to the x power dx, which is just the integral, is, you ready? Drum roll, please. E to the x, but then of course you got this plus c hanging out. You always have to have. That, my friend, is really all you're going to learn in this section of the class. We're going to work problems dealing with that. And as you can see, it's really not that bad. It's actually one of the easiest things to learn. But what you'll find is that as you work the problems, it may not quite seem that you can use these properties so easily. So let's do some. What if you have f of x is equal to e to the square root of x? Okay? And they say, find the derivative. What's the derivative of this? Okay? Well, you have to use that chain rule that we had talked about. The way I like to do it right off the bat is just write it as e to the x to the 1/2. I like to write all of my square roots as powers of 1/2. So, the derivative, remember when you take derivatives, I told you it's like multiplying. You go in. You take the derivative of the big picture, and then you multiply by the derivative of kind of the inside and the inside and the inside. The big picture going on here is the fact that you have e. Okay, so this is going to be e to the x to the 1/2. Okay, times the derivative of the exponent here. The derivative of the exponent is 1/2 x to the negative 1/2. 1/2 comes down, x 1/2 minus 1 gives you that. Okay. So really, this is the answer. I mean, there's nothing else to do. If you want to write it more in terms of the problem, then you would just have e to the square root of x over 2x, 2 times square root of x. The 2 comes from here. The square root of x comes from this x to the negative 1/2. Move it down to the bottom, and then put that square root on it. And that would basically be the answer. So you see, the derivative of the exponential is the exponential itself. So when we took the derivative, the first thing we did is said, well, this is an exponential, so I'll just write it down again. Now I got to multiply by the derivative of the exponent because it's not exactly what I have here. And then I go from there. Okay? What if you have y is equal to x times e to the 2x? Okay? Again, you have e to the power of some function of x, but you don't quite have this. Okay, it's almost the same, but it's not quite the same. So how do you take the derivative of that? Plus you have x multiplied out front. Well, you'd have to use that multiplication rule that we talked about. The first term times the derivative of the second term. So you need to find the derivative of this. The derivative of this term is simply e to the 2x because it's indestructible. But don't forget, I've got to multiply by the derivative of that exponent, which is just 2. Okay? First term times the derivative of the second term, that's what this is, plus the second term times the derivative of this first term, which is just 1. So the derivative is 2x e to the 2x plus e to the 2x. And that's it. That's the answer. The only real trick is to know that, hey, you got to use that multiplication rule, and then when you take the derivative of this here, you've got to take the big picture derivative, which ends up being itself, and then times the derivative of that exponent, and you'll get the answer there. Okay, we're going to work a whole lot of problems here so we get comfortable with this. What if you have h is equal to the square root of 1 minus e to the power of t, and you want to find the derivative of that? Well, the first thing I do when I see this kind of thing is I write it as a power with a fraction, because then I know how to take derivatives of that. So the derivative is equal to, what's the big picture here? I've got something raised to a power, a number. So I've got to use that polynomial rule. So I have 1/2, exponent comes down, times the base, which is just 1 minus e to the t, to the power of this minus 1. 1/2 minus 1 is negative 1/2, right? But you can't stop there. You've got to take the derivative of the inside. So you multiply the derivative of the inside. Derivative of 1 is 0, so you don't even write it down. The derivative of this is going to be the negative, just kind of stays out front, doesn't go anywhere. But the derivative of e to the t is not going to change, e to the t. And you could take the derivative of this exponent, but you're just going to get 1, so you don't even have to write that either. So 1/2 comes down, base, 1/2 minus 1, okay, times the derivative of the inside, which is this. And it's kind of indestructible, so it sort of hangs around like that. And if you were going to write that in terms of, get your fractions right, you would have negative e to the t, this would be on top, over 2 from this, and then the 1 minus e to the t, and you have that 1/2 power that would be transferred to the bottom. This moves to the bottom because it's a negative exponent. 2 goes down with it, and this stays up on top. I'm just showing you how to rewrite these things because different teachers are going to want them different ways. What if you had y is equal to e to the power of x times cosine of x? You see, these are getting a little bit more and more complicated. How do you take the power of the derivative of that? That's what we're trying to practice here. Well, the big picture is e raised to the power of something, of the function of x. And you know the big picture is it's indestructible. So the derivative is, you just write it down again, x times cosine of x. Okay, no problem so far. But you can't stop there. You've got to multiply by the derivative of this exponent here, of the inside. It's x times cosine of x. So it's going to be, we're going to have to use that multiplication rule. So it's the first term times the derivative of the second term. Derivative of cosine, if you look back on your chart, is negative sine of x. First times derivative of the second plus the second times the derivative of the first term, which is just 1, like that. You've essentially found the answer at this point. That's it. But you just have to kind of collect terms and simplify from there. So the way I just did it on my paper is x cosine of x times, and I just wrote this in reverse order, cosine of x minus, from this minus here, x times the sine of x. Okay? And that's really the answer. The only thing that made it tricky here is you had to do two things. You had to do the chain rule, because you had to say, okay, the derivative of the big picture, which is just the same thing, so you write it down, times the derivative of the inside. But then when you actually calculate this derivative, you had to use that multiplication rule, so it was kind of a little bit complicated to do that. So it was the first term times the derivative of the second term. Derivative of cosine is negative sine, plus the second term times the derivative of the first term. And then you just simplified that. Now, You can go back and review the rules that we've learned so far on how to take derivatives, and all of that has been covered separately, but you're putting it all together, and that's why I say this is sort of getting a little bit more advanced as far as taking derivatives. It's not because these rules are really hard. It's because you're putting together all these different things that you've learned up until now. Now let's switch gears and move to integration. Integral of e to the minus 6x dx. Obviously on a test they're not going to give you something easy like this, because that's easy. You know what the answer to that is. This looks very similar. Okay? How are you going to take that integral? Well, you're going to have to use substitution to put it in this form, like this. Okay? And we've done substitution all day long, and we use substitution already to get things beat into shape in terms of polynomials so we can integrate it. Now we're just going to use it to get this into shape so that we can use this. So let's say u is equal to negative 6x. I'm going to say u is equal to this entire exponent. So du is equal, du dx is equal to minus 6. The derivative of this is just equal to minus 6, and I think you can convince yourself that's true. So then du is equal to negative 6 dx. You just move the dx over. And then dx is negative 1 over 6 du. You just move, you divide both sides by negative 6. So this piece of information, as I did in the past section, this piece of information is very important, and this piece of information is very important. That's kind of the two important things in order to do the substitution. So when you do it, you're going to have integral of e to the u, because you define what u is here, times dx. But dx you've already defined here, so it's going to be 1/6 times du. Now you know when you have a constant in here, you can just simply pull a constant out. So this is negative 1/6 integral of e to the u du. Now looky here. It's exactly the same form. E to the u du, e to the x dx. What's the answer? I think you could do that with your eyes closed. The answer is e to the u plus a constant. But you don't want to leave the answer in terms of u. So you just simply look back at your definition. U is defined by this, so you just write it back in there. That's the answer. You see, all this stuff is really just boiling down to what kind of tricks can I use to change the integral into a form that I know, and here I've just taught you another form that you know. So you put it in your back pocket of mathematical tricks, and on the test, if you have an exponential anywhere in that integral, I would start looking at ways to beat that sucker into the shape of an exponential so that you can integrate it, and so on. And that's kind of why I was saying at the beginning of the class that derivatives are kind of mechanical. You can take derivatives. You just kind of have to keep multiplying by the derivative of the inside, and eventually you'll get to the end and there's nothing else to take the derivative of. Integrals, on the other hand, you have to use some technique to it. What do you choose your u? And then from that, you can go ahead and simplify it into something you can solve. Let's try something a little bit harder. Integral of e to the x times 1 plus e to the x to the power of 10, obviously over dx. Well, this is exactly what I told you. If I see something like this on a test, I've got exponentials, I need to try to do some substitution so that I can end up and use this property. That's what I'm going to try to do. It may not work out, but that's what I'm going to try to do. And so from experience, I kind of know what to do, but hopefully you're gaining that experience too. I'm going to say, I'm going to let u is equal to 1 plus e to the x. So then du dx, the derivative would be, derivative of 1 is 0. The derivative of e to the x is just simply e to the x. So I just write it like that. And then du is equal to e to the x dx, and then dx is 1 over e to the x du. You just divide both sides by e to the x. So again, this is the important piece of information. This is the important piece of information. So you have integral e to the x times u to the 10th power. Don't forget that. And then dx, look what I have here, 1 over e to the x du. Now look, it follows the same pattern as the other section in substitution. Make a substitution and a nice cancellation occurs, which is exactly what I want. So it's integral of u to the 10th power du. You already know how to integrate that. It's 1 over 11 u to the 11th power plus a constant. And so what you're going to end up with 1 over 11. And in the end, you don't want to have your answer in terms of u. You want to have it in terms of x. So 1 plus e to the x to the 11th power plus a constant. And that's the answer. So you just picked a substitution, you did all the mechanics, something canceled, and you ended up with an integral that you knew how to solve. And in the end, you didn't really have to use this too much. You ended up having to use the property and to know how to take that derivative, but you didn't actually integrate the exponential itself. By far, the trickiest thing is figuring out what to pick for your substitution. Integral e to the x plus 1 over e to the x, obviously dx. Your first thought here might be, let me go ahead and find the substitution. And that might work. You might be able to find one here. But the way I did it was the following. I knew immediately when I have something added up over one term on the bottom here, I know that I can write it like this. E to the x over e to the x plus 1 over e to the x dx. Let me pause here. The reason I can write it that way is because, look, this denominator is the same. If I were to add these fractions back up, the denominator would be, it'd be like 1/5 plus 2/5. Well, the denominator stays the same. The top you just add together, right? So the denominator stays the same. The top you just add together. So I can split it up like that. I can do it in reverse. Why does that help you? Well, I think you can already see why it helps you. This becomes 1, okay? And this over here becomes e to the minus x. Okay, e to the minus x, which isn't too bad. Now, the way I'm going to solve this integral is, I'm going to say this is integral of, well, what I'm going to do is, you know, when you integrate two terms that are added together, you can just simply integrate each term individually and add the results. So I'm going to integrate that first term. Integral of 1 is just simply x, right? Plus, but I haven't integrated the second term yet, e to the minus x dx. I've integrated the first term, and this is the answer, but I haven't integrated the second term, okay? This is the integral of e to the minus x. I know what integral of e to the positive x is, but I haven't told you what the integral of e to the negative x is. So let's use our trusty substitution thing. I'm going to say u is equal to negative x, du is equal to negative 1, du dx is equal to negative 1, the derivative. So then du is equal to negative dx. And just multiply both sides by dx. So I'm going to say this is equal to the integral of e to the u, this is equal to u, times dx, which is simply negative 1 times du. Okay? Dx is negative 1 times du from this here. Okay? So then you'll have x, this negative 1, I'm going to pull it outside. This is all multiplied together. I'm going to pull it outside the integral like you can pull any constant out. I'm just going to put a minus sign here. E to the u du. So you're going to have x minus, look, this integral e to the u du, well, it's the same thing here. It's an indestructible function, so I'm going to put e to the u plus a constant. The only thing remaining is to plug in for u. U is defined by this, negative x plus a constant. So this would be the answer, x minus e to the minus x plus a constant. And I'm going to do one final problem to give you a little bit of experience with this. Integral of x over e to the x squared, e to the x squared dx. Well, you certainly don't know how to do that, but you want to get it into something where you can use some of these properties here, and you're going to have to use your substitution. So again, you're going to gain experience as you go, but I'm going to say u is equal to x squared. because I want it to be in terms of e to the u at the end. So du dx is equal to 2x. You just take the derivative of this, you get 2x. So then du is equal to 2x dx multiplied by dx, and then dx, made a small mistake here. This is du, like this. So then dx is 1 over 2x times du. Now let's see if this helps us out. Integral of x over e to the x squared, but then u is x squared, so it's going to be e to the u times dx, but dx I've defined as 1 over 2x du. Well, immediately I can see I've done a good deed for the day because this x cancels with that x. And then my integral is going to be without any x at all, which is what I want. This 1/2 I'm going to pull out of the integral, and I'm going to have 1 over e to the u du. Okay? Now, you want to be able to use this, so let's go ahead and move it up to see what we have. E to the negative u du. I just moved it up without, so you didn't have a fraction here. But you see I still have a problem because I have this negative u. It's an integral of e to the negative u, and clearly I don't know the answer to that. I know the integral of e to the positive u. So you're going to have to do something. So my suggestion is do another substitution. There's nothing that says you can't do that. So I'm going to use the variable s. S is equal to negative u. I'm just doing another substitution as if this were the original problem. So to start over, you've gotten to this point, figure out what this is. ds du, the derivative of s with respect to u, is just negative 1. Derivative of this is negative 1. So then ds is equal to negative du. Okay? So then you're going to have 1/2 integral e to the negative u, but that's just going to be s, times du. Du, if you move this over here, is just going to be negative 1 times ds. So the negative 1 can come out, so you can have negative 1/2 integral e to the s ds, e to the s ds. Now it's exactly in the form that you need it. So then you just say 1/2 e to the s plus a constant. But then you don't want to leave your formula in terms of s, so you plug in for s. S is equal to negative u, but again you don't want to leave it in terms of u, so you plug in for u. Negative 1/2 e to the negative u, which is this, plus a constant. And that would be the answer right there. So this one looked a little bit harder, okay, and that's why I'm picking it, because this is the last problem in the section, because it's one of the harder ones that I chose to do. So you have this, you choose your u, you get it all down, get your dx, you get this nice cancellation so you know you're on the right track. But then what you're left with is 1 over e to the u, which doesn't quite fit in with this, so you can't really do that right away. You make it as an e to the negative u, and you're stumped for a second, and you say, well, geez, I don't know what to do. It's not the same. Well, don't freak out and just guess. Sit there and beat it into shape. Pick another substitution. That it's equal to negative u. Now I have the thing in terms of e to the s. And then when I do this here, then this constant just comes out. I've got an integral exactly in terms of what I need, and so then the answer will be in terms of s. You plug in what you knew for s, now it's in terms of u, and you plug in what you defined for u, and it's back in terms of the original function that you needed in the first place.